Recording.
Okay.
So thank you, Dr. Reka, for introducing me to the class. And hello, everyone. My name is Shenghan Guo. It's my great pleasure to be here and give you a brief talk about my research. I will not go to every detail of my research project, but I chose a very interesting topic that I'm working on right now. And yeah, that's what I'm going to talk today. Deep learning enabled thermal signature prediction for laser metal deposition. Why it doesn't work? So I will start with the research background, then the motivation and objective, and then I will elaborate on the methodology development, then present you some case study results. I will finally wrap up this talk with some concluding remarks. So laser metal deposition, also named direct energy deposition, is a laser-based additive manufacturing process that uses the laser beam to generate the heat for melting and consolidating the added material powder to build a part. During the process, a laser beam is used as the heat resource, and it constantly injects the material powder onto the thin stage and melting it along the way. There will be a melt pool created at the contact of the part and the laser beam. The melt pool is the major source of thermodynamics that is created during the process. It is highly related to the part quality after the process is done. So as an additive manufacturing process, LMB is advantages in its flexible design and fast manufacturing. It has a lot of potentials for customized production. For example, the knee implant and teeth crown. Also, it is very useful for building high value, low demand products, such as the advanced turboprop engine for aircraft propeller. Compared to other additive manufacturing processes, LMB is also advantages for its high build-up rate and density. Also, it is able to build 3D surface adaptively and has very gradient layers. This is a simple animation I made to demonstrate the LMB process of thin-walled part. Initially, the CNC stage starts with relative and move relatives to the laser deposition head, like this one. That is, the laser deposition head would inject the material powder onto the CNC stage and finish one layer in this way. Then, after the first layer is built, the laser deposition head would increment upward slightly, and the CNC stage would return to its initial location. Next, the CNC stage would repeat this process again with the laser deposition head constantly inject the material powder onto the first layer. That is how the second layer is built. So this whole process would be continuously repeated until multiple layers are accumulated to fulfill the part dimension that is predefined by the practitioner. Well, like many advanced manufacturing applications, the LMB applications has a major concern, the part quality. So it is subject to process instability and product defects. Nowadays, with the advancements of sensing technology, practitioners would want to monitor the process in real time. They collect the thermal imaging data during the build process. This is a demonstration. This is a demonstration of data collection system in a lab experiment. We put a parameter next to the laser deposition head. this parameter would move along with the deposition head during the build process, and it captures images for this mel pool directly from the top. And we see there's the sample images from the data collection. This is the thermal images from the parameter. The red part is the mel pool. Essentially, this data is a grayscale image. Each pixel represents the temperature of the part surface. And the brighter the color, the higher the temperature. This image is the same type of data, but I visualized it with RGB color for better presentation. We can see that the center of the mel pool has the highest temperature, and the further away from the center, the lower the temperature. Studies have proven that the thermodynamics of mel pool, or the temperature, it is very critical, and any anomaly of the mel pool would result in defects of the finished part. For example, there are some typical microstructural defects that we commonly see in LMB, like the porosity, lack of fusion, and this is like a surface cracks. So one thing really important is that we want to monitor the thermodynamics of mel pool in real time so we can detect the anomalies. The implication here is that how we have the thermal images of mel pool, right? So this is the image. Sometimes we also refer to this as the thermal signature of LMB. The availability of these thermal signatures is very critical for real-time monitoring of the LMB process and control the product quality. But this is not a very easy task. Because we have this limited data availability. If we're talking about a lab experiment, it might be possible to collect those in-situ thermal signatures we just saw. But if it is real-world application of LMB, this is very challenging. First of all, in industry practice, the part produced with LMB is usually with low volume. The low volume production limited the data we generated from the application. Also, many commercialized LMD machine systems, they do not have the built-in imaging sensor to collect the thermal signatures. That is why we have limited data from LMD. What we really need to do here is augment the thermal data availability so we can do the real-time process monitoring. Any questions? In state of the art for thermal signature prediction, there are two branches of method. One is physics-based method. Some of you may have known this, like a finite element analysis and related physical method for simulating a manufacturing process and generate some simulation data to choose to monitor that process. That is the physics-based method, and it is a common adopted method for thermal signature prediction. But a major concern with this type of method is their cost and time demanded for developing this kind of method. So recently, researchers for LMB, they have been looking for data-driven methods. For example, we have this generative adversarial nets. That is a deep learning model that is able to generate synthesized images. When we think of this thermal signature prediction task, we essentially want to generate thermal images of mel pool, and that is an image generation task. That's why I would propose to start from generative adversarial net. This is a bright starting point for developing method to augment the thermal signature data. The objective of this research is to develop such a method based on GAN, so we can predict the thermal signatures of our LMB and make more thermal data available. Then we can facilitate in-situ process monitoring. So to give you a better idea of this starting point, I'd like to briefly explain what generative adversarial net is. GAN is a machine learning system, consists of two neural networks. One is a generator or generative model G, and the other is discriminative model D. These two models or these two neural networks, they compete with each other in an image generation game. So when we have some real data, the generator would learn the statistical properties of this real imaging data. Then it synthesizes images by adding those statistical properties to a random noise or noise vector. That would enable it to generate a fake image. Then we have the discriminator. This discriminator takes that image and make a decision whether this is a real image or a fake image. There is a computation going on. The generator and discriminator, they compete with each other. So eventually, the generator wants to generate images that are so real, the discriminator could not tell they are fake image. That's the purpose. With this mechanism, GAN is capable of synthesize very high quality or very real images. And it has been used in a variety of applications involving this kind of image synthesis, like video games, fine arts, fashion, and the advertising industry. Now, getting back to our LMD, we want to start with GAN and use it for predicting thermal signatures. But there is a challenge because we have this fundamental physical phenomenon in LMD, the layering effect. We know that when we build a part with LMD, we accumulate layers, right? So when multiple layers are accumulated, they have intensive heat transfer across layers. The result is that thermal dynamics of melt pool in different layers show different characteristics. When we look at the melt pool in, say, layer 1, it is not that stable. But as we accumulate more and more layers, the melt pool dynamics are getting more and more stabilized. The implication here is that the melt pool thermodynamic is dependent on the layer index. Equivalently, when we predict the thermal signature, we want to make predictions conditionally on the layer index. But this is beyond the capability of the conventional generative adversarial nets, and that is our challenge. To handle this challenge, I proposed this LMBCG model. It is a more advanced version and customized for thermal signature prediction upon the conventional GAN. So first of all, it uses an encoder to get an input to learn from real images from a finished LMB part. This is the model architecture of that encoder. You see, it is like a convolutional net, and it intakes the image from a real image from layer L, and then learn from it, output a noise vector Z star. Another component of LMBCG is a conditional GAN. This is a little bit more complicated. The CGN consists of D, a generator G, and a discriminator D. And it will take the latent vector Z output by the encoder to generate an image conditionally on the layer index, on a target layer index we defined by the user. This task is fulfilled in a minimax game. You see this loss function, right? So there is the generator G. It maps the latent vector from our encoder to a predicted thermal image for the target layer. And then the discriminator D would map this generated image to a decision whether this is a true thermal image or a fake thermal image. With this loss function, the first item would minimize the likelihood of rejecting a true image. And the second item minimizes the likelihood of accepting a fake image. With this minimized game going on and on, eventually, the LMBCG model is able to predict thermal signature for the target layer with very high realness. This is the architecture for the generator G and discriminator D. You see that the generator intakes the latent vector from the encoder and also the target layer given by the user, map them to a synthesized image for the target layer. And then the discriminator D, it intakes the generated image and map that to a decision whether the image is a true image or a fake image. I won't go through all the model parameters, but to present this architecture to give you a flavor. With this LMBCG model, we would be able to make thermal signature prediction for target layer of an in-process part or part being printed. This model is applied in a case study. Recall that I showed you some images previously for LMB symbol part. I used that data to train the LMBCG, and there was totally 1,200 thermal images, around 20 to 25 images from each layer. I will show the results shortly, but before that, there is an additional component in this work. That is the physics-guided image selection. So think about this. The LMBCG model I just proposed, that is purely data-driven. It is trained with all the imaging data, right? But it is respectful to the fundamental layering effect in LMD. But ultimately, it still synthesizes image from some noise data. And we would be concerned whether the generated thermal signatures that are fully physically valid. It is possible that the thermal signature are not that valid, right? So consider that we have some existing physical resources, say a finite element model that is built for the LMD application previously. Why not we use that physical resources as a benchmark to calibrate our thermal signature prediction from LMBCG? That would be good, right? To do this, I proposed this PGS control chart. For example, we have the training images from a finished LMD part, and we have the physical resources, for example, an FEA model, and it generates a simulated image of Melpool. We can calculate their distance, specifically a Frobenius norm. Some of you may know it. This is to characterize the difference between the training data and the physics benchmark. With that, we can calculate a criterion, which is the control limit here. This is like a criterion whether the image, the prediction would be physically valid or not. If a physically valid image, then the Frobenius norm should be below this control limit. Then when we use LMBCG for prediction, we have the predicted image like this. Again, we measure the difference between predicted image and the FEA benchmark. That will give us the Frobenius norm between them and visualized as the blue dots in this control chart. We compare the magnitude or the height of the blue dot with the control limit, right? Like I said. So if it is below the control limit, then that's good. This prediction is physically valid and we preserve it. Otherwise, if it is above the upper control limit, it is physically invalid. We should discard that. And again, we do the prediction to obtain another predicted image. Now, we have all the components ready. This is a flow chart demonstrating how they work together. In the training stage, we obtain some thermal images, real thermal images for a finished LMD part. We use that image to train the LMBCG model. It consists of the encoder E and CGN, as we mentioned before. Next, when the model is ready, we use the model for thermal signature prediction. Suppose we are building a new part. Then we have the real thermal signatures from early layer, for example, layer 10. Now we want to predict for layer 50. We input this real image to the established LMBCG model. First, the encoder would output a latent vector Z, and then this latent vector Z star would be input to CGN to synthesize an image for layer 50. Okay. If we have some prior physical resources, we develop this PGS control chart and use that to evaluate the physical validity of the prediction. If it is valid, then we have the predicted image for layer 50. The predicted image should be so real, and we cannot visually tell the difference between the real data. Now, I'd like to present some results from the prediction. This is like the real data-based results. I input a layer 1 image from a real part and then generate thermal signatures for layer 1, 10, 20, up to layer 60. Only this one is the real image, and all the rest, they are images generated by LMBCG. And you can hardly tell that like they are fake image, right? Like by just looking at them, because they are so real. If you do a more detailed comparison with say another image from layer 60, this image in layer 60 is almost the same with the real one. We say that this method we developed here, it is very effective. It respects the layering effect of LMB processes and allow early access to thermal images in future layers for in-process part. That really augment the data availability for LMB and facilitate in-process monitoring. Now, I'd like to conclude my talk today. LMBCG model is developed for thermal signature prediction, and we propose the PGS to secure the physical validity of the predicted thermal images. Of course, this whole work, they have facilitated in-situ process monitoring and the quality control by augmenting the data availability. Overall, this research has been completed, but there are some very interesting future directions that I'd like to look at in near future. That's why I'm here, right, to present you this work. And any of you, if you're interested, you can feel free to contact me. This is my email and phone number. My office is in Tech Center 153. Please feel free to drop by my office or send me emails.
Any questions from the audience? Yeah. Yes, ma'am. Is your research also concerned with the control system aspect of this? Once you generate the model, generate the CAD model, do you use that to change the laser power or the speed of the layering, the actual LMB process?
So this research is mostly data driven.
Okay.
And I think what you mentioned, the control system, it can be the PGS part, like the control chart, right? That is some potential in the future. If some students of mine would be interested in working on that, I would fully support.
I'm interested. Sure. Any other questions? Because I have some students here, they are taking my linear algebra class, and I'm teaching them data-driven modeling and technique.
Yeah.
So you're welcome to talk to Pustaka related to the research opportunity that she has.
Yeah.
Any questions from online students? Questions from online students?
Nope, that's so quiet.
Okay, then thank you so much for coming, Pustaka.
Thank you.
And contact you.
Yeah, sure.
Please note down.
Yeah.
Address.
Can I make one last comment?
Yes.
So my research mainly focuses on data-driven solutions for smart manufacturing. If you are really interested in data, machine learning, and you're very good at coding, especially R or Python, I would really hope you can contact me, and we will have great mutual interest. Thank you so much.
Do you take students with MATLAB experience? Because most of
yeah, of
MATLAB
course.
is good.
Yes.
Because we use MATLAB in this course and other.
I believe any programming foundation should be good, and it should not be a problem as long as you know coding, yeah. And you like data.
Awesome. Thank you so much.
Thank you. Thank you for this opportunity.
Yeah. You got everything,
Yeah,
right?
yeah, I got everything.
Okay, awesome.
Thank you
So much.
so much.
Okay. So fortunately or unfortunately, this would be the last seminar for this semester for robotics 1. So now you won't have any external speakers. You are left just with me. So I just want to give you a quick update. I have postponed the deadline for the next assignment. So it will be due, I think, after 10 days. So, and I promise that I will cover the material that you need to finish that assignment into the next few classes. Today, I'm going to start with velocity analysis. And let me be absolutely clear. The material that I'm going to discuss today onwards is super duper important, because I'm going to teach you how to perform the velocity analysis on complex manipulators. Then I'm going to teach you a technique which is called as Lagrange method. That Lagrange method can be used to find the differential equations of any three-dimensional dynamical system. Okay, but please understand, once I solve some simple cases using Lagrangian dynamics by hand, I'm going to teach you how to code it in MATLAB. And you may hate me now, but you'll thank me later, because what it means is you would be able to understand the dynamics of any three-dimensional robotic or any other system. And I'm going to give you a MATLAB code, and I will walk through some examples, initially simple spring mass problems and then robotic actuators. So you can actually program that in MATLAB, and MATLAB would do all the coding, come up with the differential equations of motion, finally numerically integrate those differential equations of motion and give you solution. These techniques are very, very powerful. So please don't miss any of these classes. Our seminars are done for this semester, but now onwards, the material that we are going to discuss, we are going to first finish velocity analysis. That way you can find the kinetic velocity of your robotic manipulator. Then we will talk about formulating the Lagrangian. Then we will formulate coding mechanism wherein you can code that Lagrangian inside MATLAB. And when that is done, you will run the script so that the MATLAB would find the numerical, the differential equations of motion, and it will solve those differential equations of motions, and it will plot the differential equations of motion. There is one part I want to add that I didn't teach in last class, is actually interfacing those solutions with some sort of sim mechanics demo, which means basically you will see your robot in action. So depending upon time, either I may add that I will teach this, or I will add some supplemental resources that would allow you to do that. Once that is done, you will realize that many robotic systems are unstable. Then we will study the control. How do you interface controller algorithms so that your robot can be controlled? So what I'm going to do now is, in today's class, I'm going to start the velocity analysis. So all this material is super duper important. What happened to Joe? So far we have talked about the forward kinematics. We talked about the inverse kinematics. Now, what is the crux of forward kinematics? At the end of the day, yeah. What is not sharing? Yeah. Okay. So what is the purpose of forward kinematics? The fundamental purpose of forward kinematics is given the joint variables. What? Shows on my screen. Okay. All right. Just a second. I know what's happening. Okay. Now you should be able to see the screen. Okay. The fundamental purpose of forward kinematics is this. Given joint variables, find Px, Py, and Pz. Also, find the orientations of the end effector. This orientation is known as a rotation matrix. So what does that mean? If you look at the homogeneous transformation, you have Px, Py, Pz over here, and you have a rotation matrix. For the time being, I'm going to call this 0Rn. This rotation matrix is over here. Now, what we want to do is from this displacement data. So these are the displacements. So from this displacement data, I want to find out the velocity. And the way the velocities are found is by simple differentiation. So what I want to do is, let's take a very simple example of a single actuator. So I have a robot, and this robot, it's something like this, wherein this is θ1. You have coordinate system. I'm going to call this Z0. I'm going to call this X0. And this is Y0. And then what I'm going to do is, I'm going to have X1, Z1, and Y1. Now, you know what to do, right? First, find the rotation matrix, then find the projection matrix, then formulate the homogeneous transformation. What I'm going to do is, for this guy, I'm going to write down the homogeneous transformation directly. This is the end effector. And you can correct me if I'm wrong. 0H1. This is going to be cosine θ1 minus sine θ1, sine θ1, cosine θ1, 0, 0, 0, 0, 1, 0, 0, 0. And here, can someone tell me what would be Px, what would be Py, and what would be, this is, I'm going to call A1, and I'm going to call this A2. I will write this. Correct me if I'm wrong. Yeah, A2 cosine θ1 A2 sine theta 1 A1, and then here there will be 1. Do you agree with me? Now I know the values of Px, Py, and Pz. I want to find now the velocities. So how do we find the velocities? The simple way to find velocity is to differentiate. Now, one thing that I want to understand is amongst these, what is changing and what is constant. Now, please understand this problem is super duper important because your assignment number 4 is exactly the same problem. So please pay attention. I'm going to make a small change, and the solution will reveal itself. Reveal itself. And then, okay. So now please understand A2 is a constant. A2 is a constant. A1 is a constant. The only thing that is changing here is theta 1. Do you agree with me? But so what I'm going to do is I'm going to find out d by dt of px. But please note, d by dt of px, and I'm going to write this for the very first time in case px is the function of theta and theta is function of t. I am differentiating not with respect to theta, but I'm differentiating with respect to t. What does that mean? It means I need to use the chain rule. So dpx by d theta 1 multiplied by d theta 1 by dt. So what does it mean? It means A2 derivative of cosine theta 1 becomes minus sine theta 1, and derivative of theta 1 is theta 1 dot. Everyone understood this? Yes.
What is sigma 1 dot means?
Dot means this. So derivative with respect to time, single derivative is 1 dot, double derivative is 2 dots, triple derivative with respect to time is 3 dots. Does it make sense? Okay. Now this gonna be minus A2 sine theta 1 dot. Don't forget theta 1 dot. That is super duper important. Next part is I'm gonna do d by dt of py. Please note py is also function of theta 1. So what I need to do is dpy by d theta 1 multiplied by d theta 1 divided by dt. This is the chain rule. And this equation now becomes, I'm going to write this here, A2 cosine theta 1 dot. Do you agree with me? But last but not least, what happens if I were to take d by dt of pz? Please note d by dt of pz is going to be 0 because a1 is a constant. Do you agree with me? Now, what I'm going to do is I'm going to write this equation in terms of what is called as Jacobian. So let me say what that means. So I'm going to write this, or at least I will try to write this in some sort of a matrix vector type of form. So I want to write this equation something like this: px dot py dot pz dot is the vector on the left hand side is equal to one matrix. And it is super duper important that this matrix doesn't have to be square. This matrix can be a rectangular matrix multiplied by the joint variables. Are you with me so far? Multiplied by the joint variables. And I'm going to write this down, something like this. Now, I want you, based on this equation that we derived a minute ago, tell me the joint variable in that equation for velocity. What is the joint variable? The variable that is changing. D theta, so that is theta 1 dot. Everyone agrees? Nothing else changes. So I have theta 1 dot. Now, what should I write in this matrix? I should write A2 minus A2 sine theta 1 so minus A2 sine theta 1. Then what I should write? Actually, I should, let me make it a little bit, now let me spread this out, because this concept is very important. Even though this matrix will be unpopulated, but this is very important. So A sine theta 1, here there will be 0, here there will be 0. Then I'm going to have A2 sine theta 1 dot. So this is A2 sine theta 1 dot. Then I'm going to have A2 cosine theta 1, A2 cosine theta 1 dot. And here everything is 0. So in other words, I don't have to write this as a complete matrix. I can just write this. This is very important. I can just write this as maybe a partial matrix. I just eliminate all the zeros and get done with it. But this is called as the Jacobian. And these are called as joint velocities. And some of you may ask me, does this make sense? And we will see in just a minute if this makes sense. So what I want you to do is, I want you to look at this single degree of freedom robot arm from top. So imagine you're looking from top. When you look from top, so what you would observe? You would observe that robot arm, something like this. This angle is theta 1. This angle is theta 1. And you would observe there are two directions in which, let me just see here. So you have A1 cosine theta 1. Okay, so what you have is, you have in two directions. So you have a component of velocity in this direction, which is, so basically this arm is going like this. So if you were to square these and add, and this is for just for the reference, if you were to square these and add, you would observe the total velocity is going to be A2 square theta 1 dot square, which is the same equation as R square omega square. And if you multiply that by 1/2 mass, that gives you the kinetic energy. Now, so what you have here is, you have a component of this velocity in the vertical direction, and you have a component of this velocity in the horizontal direction. I just want to make sure that you understand this. So Let me explain this once again for my own satisfaction. We look at the coordinate system. The coordinate system, when you look from top, is like this. When I look at the coordinate system, oops. You look coordinate system. Okay, so I missed the last slide, but let me explain what I was trying to explain. If you look at the coordinate system, from top, this is what you're going to observe. This is going to be your x naught, and this is going to be your y naught. Now I want you to understand the velocity is in this direction, and this velocity is nothing but this distance, which is a2, multiplied by theta 1 dot. This angle is theta 1. So if you were to find the velocity is given as a2 theta 1 dot. Now this velocity has two components, and this velocity has a vertical component, and this velocity has a horizontal component. So let me show you the vector diagram of this velocity. So you have a velocity, a component of velocity, which is going in the vertical direction, and you have a component of velocity which is going in the horizontal direction. Look at the vertical component of velocity. Vertical component of velocity, this guy is py dot. This py dot is in the same direction as y0. Do you agree with me? Py dot is in the same direction as y0, which is your initial coordinate frame. But look at px dot. Look at px dot. This px dot is opposite to x0. Do you agree with me? That's why when you look at the equation that we derived for px dot and py dot, px dot was minus a2 sine theta 1 dot, py dot was a2 cosine theta 1 dot, and pz dot was equal to 0. So in other words, if you look at the interpretation of the Jacobian that we just derived, you have px dot, py dot, pz dot, this equation can be written as minus a2 sine theta 1, a2 cosine theta 1, 0 multiplied by theta 1 dot. So you have a Jacobian and you have a joint velocity vector. This is related to the linear velocities. But please understand, this robot has angular velocities as well. This is rotating. So how do we deal with the angular velocities? And remember this, every time you want to find out the angular velocity of end effector, that you will do a lot. It's super duper simple. Look at your H01 matrix. Your H01 matrix for this robot is cosine theta 1 minus sine theta 1, sine theta 1, cosine theta 1, 0, 0, 0, 0, 1, 0, 0, 0, 1, and you have Px, Py, and Pz here. Pz. Now, we didn't do this process here, but this rotation matrix, and this is super duper important. This rotation matrix is basically the product of two matrices. The product is 0R1 multiplied by the projection matrix. Do you agree with me? In this particular case, since the 0th coordinate frame and the first coordinate frame, they aligned, the projection matrix was identity. Everybody understood this? But many a times, yeah. Can you see that this 0th matrix, the projection, this 0th coordinate system, x0, y0, z0, is aligned with x1, z1, and y1. That's why your projection matrix is identity. 1, 1, 1 on the diagonals. So that's why you're going to get this rotation matrix. Now, the next problem that I want to state here, and I want you to remember this very, very carefully. I want to find out omega x, omega y, and omega z. What are these omega x, omega y, and omega z? Those are the angular velocities of end effector. This procedure is going to remain the same whether you have 1 degree of freedom arm, 2 degree of freedom arm, 5 degree of freedom arm, or 100 degree of freedom arm. So what you should do is, I want to find out omega x, omega y, omega z. Px, py, pz are the velocities of end effector. Omega x, omega y, omega z are the angular velocities of end effector. The angular velocity of the end effector is given as 0r1, and this 0r1 is coming from 0h1. So this contains the projection matrix. Everyone please remember this. Your 0r1, this guy, is just the rotation transformation. But when you multiplied that by the projection matrix, this became, so I'm going to just call this R bar, not R dot, R bar. So this is the rotation transformation. Multiply that by the joint angular velocity. So, and this is very important. So I want you to think about where the joint angular velocity is. Can you see that the joint that is actually so actually let me take it back just a second. I don't want to go there in advance. So okay, so first of all, here the rotation matrix has to come. Right now the rotation is theta 1. This rotation is about z0. Okay, this rotation is about z0. So omega x, omega z is 0 r0 multiplied by 0 0 theta 1 dot, because this rotation is about z0. What is 0r0? 0r0 is the projection of the zeroth frame on the frame itself. So this is going to be 1 0 0 0 1 0 0 0 1, and I will be, and then you are gonna multiply this with 0 0 theta 1 dot. That would tell me that for this robot only angular velocity is about z-axis. Everyone understood this? Everyone understood this? Now, at this point, I want to extend this discussion a little bit. Okay, I want to extend this discussion a little bit. Now, what I want to do is, instead of end effector being here, what I have is I have another revolute joint here. Instead of end effector being at where the frame Z1 is, there is another revolute joint, and that revolute joint has, say, theta 2, and my end effector is something like, I want you to imagine end effector is on the axis. The end effector is on the axis of the second revolute joint. Do you agree with me? When my end effector is on the axis of the second revolute joint, Px, Py, and Pz are not going to change.
PZ gets a little higher.
Yeah, okay, yeah. Pz, yeah, okay. I agree. Pz gets a little. I agree. So Px, Py, and Pz will change. Px and Py are not going to change. You agree with me? In other words, this is the key point that I want to make. Px dot, Py dot, and Pz dot are not going to change. You agree with me?
Yes.
And I want you to visualize, if you don't understand the actual situation here, imagine you are standing over here. And now this joint rotates by theta 2. This joint starts rotating by theta 2. Do you agree with me? Your angular velocity is no longer going to be theta 1 dot. Do you agree with me? Because it's like a merry-go-round. You have one robot arm, you're standing here, but this is rotating. Along with that, this guy is also rotating. So your angular velocity will not be theta 1 dot, it will not be theta 2 dot. It will be some combination of these two. Do you agree with me? So if I want to address this problem, how would I do this? Procedure is exactly same. Now, how many joints do I have? 2 joints. So I'm gonna add one more matrix. This rotation about joint number, so Z1. Do you agree with me? This rotation is about Z1. So I'm gonna write here 0 0 theta 2 dot. And this rotation matrix will go here. So this will become cosine theta 1 minus sine theta 1, 0, sine theta 1, cosine theta 1, 0, 0, 0, 1. Everyone understood this? The first rotation was about the 0th joint, Z0. So the rotation matrix that we grabbed was 0 R 0. Everyone understood this? Second rotation is about Z1, 1. So the rotation matrix that we grab is 0 R 1. Now, I was trying to take the shortcut earlier, but now please understand, when I expand all this, what do I get? When I expand all this, omega x is 0, omega y is 0, but omega z is theta 1 dot plus theta 2 dot. You agree with me? What it means, now let's identify. Imagine that you are on the top of the second joint. Second joint theta 2 dot is 0. So what would be your angular velocity? Your angular velocity will only be the angular velocity of the first joint. Imagine the first joint is stationary, but the second joint is rotating. What would be your angular velocity? Theta 2 dot. Please note, there is no rotation velocity about x1 or y1 because that joint is not rotating about x1 or y1. Everyone understood this? So the final angular velocity will be about theta, which will be theta 1 dot plus theta 2 dot. And this is something I want you to remember all the time. Somebody may ask me, angular velocity is good, but this angular velocity is defined with respect to what? All the velocities, angular or linear, they are defined in terms of the fixed inertial zeroth frame. So which means omega x is about x0. Omega, and this is very important, I need to write that down. Omega x is about x0. Omega y is about y0. And omega z is about z0. Everyone understood this? This is absolutely important. Px dot is along x0. Py dot is along y0. Pz is along z0. Everyone understood this? Yeah. Question. Rightmost theta be theta rightmost. Which rightmost theta? This should be theta 2 dot, right? Theta 2.
I think he's asking if it's because it's in the previous one, is it required to have an addition of theta 1 dot plus theta 2?
Yeah, so basically what you can do is no, I didn't understand. What is this?
I think what they're asking is like, is it 2 dot?
Oh, there is, okay, hold on, guys. There is no rotation matrix related to theta 2. So this has to be theta 1. This is theta 1.
Yeah, the next vector, I guess they're confused, is it theta 2 or theta 1?
This is theta 2. Oh, actually this is theta. Oh, you are asking this. What is this?
Yep.
This is the rotation of this guy, which means the time derivative of theta 2. So this is theta, if I write this down correctly, this is theta 2 dot. This is theta 1 dot. This is the rotation about z0. This is the rotation about z1. Okay, good. Now, what I want to do is, I want to take the same problem. Everyone understood that what I did, I added a rotation joint and we found out the angular velocity. I can do the exact same thing. I can add another arm and then it would become a 2 degree of freedom robot arm. But what you will do is, you will do the exact same thing. Find out the px, py, pz and take the derivative. But how would you do this? Let me make this problem similar to your assignment problem. That way you can get started. So in your assignment problem, you have something like this. Right? This is the problem. Now this problem, in theory, is similar to this problem, except this length, which was initially fixed, is now changing. And this distance say I'm gonna call this distance D, and I'm gonna call this distance A2, and I'm gonna call this distance A1. And once you are done with your homogeneous transformation matrix, I think you are gonna get 0 edge. So this is 0th frame. Then you are gonna have the first frame, and then you are gonna have the second frame. So 0, so 0, 1, 2. 0 H2 is gonna look like this. And you can correct me if I'm wrong. Cosine theta 1 minus sine theta 1, sine theta 1, cosine theta 1, 0, 0, 0, 0, 1, 0, 0, 0. And here you will see it will be A2 sine, so this will look like A2 sine theta 1. So A2, yeah, A2, yes, A2 plus D cosine theta 1. Then you're going to have A2 plus D sine theta 1. And this would be A1. This will be 1. You agree with me? Now here, if I want to find out Px, it's A2 cosine theta 1 plus D cosine theta 1. Now, please note, there are two variables. D is changing with respect to time. Do you agree with me? Because D is the extension of the cylinder. So D is a function of T. And theta 1 is also a function of T. So Px dot is A2 cosine becomes sine theta 1 dot plus, now you have D and you have theta 1. So this would become D dot cosine theta 1 plus D minus sine theta 1 dot. Please note, there are two variables. That's why we got two terms. So the derivative of first variable, second variable is treated as constant. Derivative of second variable, first variable treated as constant. So then if you go to Py dot is gonna look like plus A2 cosine theta 1 dot plus this is gonna become D dot cosine theta 1 sine theta 1, sorry, sine theta 1. Okay. Sine theta 1 plus D cosine theta 1 dot, and Pz dot is going to become 0. This can be written as Px dot, Py dot, Pz dot is equal to a matrix. And now how many joint variables we have? 2. So this should be theta 1 dot D1 dot. And then you can say this is going to be a minus A2 sine theta 1 plus minus D, no, minus d sine theta 1. The second term is gonna be a2 cosine theta 1 plus d cosine theta 1. And here there will be zeros. And here d1, this will become cosine theta 1, and this will become sine theta 1. So this is going to be, and please note, this is one term. So when you multiply first row, first column, first row, second column, you get the answer on the left. And in this particular problem, the second joint does not have any rotation. So which means there is no theta. Do you agree with me? So the angular velocity equations that we derived for the first problem would remain the same. With that, I'm gonna stop here and be happy to answer any questions you may have. Yeah. What? Did I make a mistake there? D cosine theta 1, which, what did I do? Oh, matrix. So first row, first column, that gives you the very first equation. Second row, first column gives you the second equation. Okay, you want me to expand this? So minus a2 sine theta 1 minus d sine theta 1 multiplied by theta 1 dot is this term, right? Plus c cosine theta 2 is this term, right?
When we multiply it satisfies.
Question is metric multiplication. That gives you this. This is this plus this. And it's second, first row cosine theta 1 multiplied by different term. So when you multiply this row, this column, you get this guy. You multiply this row, this column. Centimeters.
Let's say there were multiple joints. So we take 0 or 0, which will be identity. Right? And this will be